Okay, so I'm thinking about the upcoming projects, and last time our projects were really the report on in PowerPoint, producing a PowerPoint report. This one there'll be a PowerPoint associated with it, but a large part of the project will be producing Excel spreadsheet tools that you can use. And I've come up with a list that you can select from, and maybe you need to do like 3 of these out of a list of 5 or 6, so that you kind of get to choose the things that you're interested in. One of those would be using the equations that we have in the notes to produce either like a PX phase diagram or a TX phase diagram. And that way you could type in the boiling points and so on, and you could put in the vapor pressures of your various components and look at the total vapor pressure, maybe with the Margulies equation, so that you could determine if there was some azeotropy or something like that. So that's the one possibility. Another possibility would be some of the things that we're doing today. So this is the specifics of using the Hansen solubility parameters in determining the solubility of a substance. And so we're going to go over that in great detail today. Doing any of the other thermodynamic spreadsheet calculations that we're going to do. So on Friday, we're going to talk about group additivity. That one can be done in a spreadsheet, but I'm telling you, there's a few things that are as tedious as that, because I'll show you why. It's not so great. The third one on Monday would be the quantitative structure property relationship related to combustion enthalpy. And that one is really fun. So that's a PChem 2 lab. So we'll be looking at that. That's right. Yeah, so we'll be looking at that because I think it teaches some really valuable principles that we can use to compute the combustion enthalpy, but more so, there's also one for molar volume. So we can compute molar volumes, which allows us to compute densities, which also are related to these Hansen solubility parameters. So there's lots of potential calculations, and I'd like you guys to be adept at producing Excel spreadsheet tools that you can use in your work, either for your thesis or even later on. Had a student get a promotion. Well, a couple of students have written back and said that their Excel skills from the PChem courses that they took here led directly to promotions. One was he was in oil and gas in Pennsylvania, and he was just tired of trying to figure out all these conversions from barrels of oil to liters, to using the density to see how much weight those things would have, and so on. And so he just made a spreadsheet tool that had all these conversions built in, even the geometries and shapes of the containers, and how much is a 8-foot diameter tank that's 12 feet tall, how much oil can that hold, and so those are the kinds of questions that he had, and so he had a lot of geometric calculations that he could put in. You could put in the diameter of a tank and the height of the tank and so on, and you calculate the volume in liters, the volume in gallons, the mass of the oil that's in there, and so on. So he just did it for his own work, and then people in the company were like, "Hey, can you give me that spreadsheet?" So he was immediately sort of his reputation was really elevated, just because he was able to do these calculations that most people can do by calculator if they've got all the little conversions. But it's incredibly tedious to constantly have to go dig through your files. Where are my conversions? Where's my conversion sheet? And to sit there and do it every time on the calculator, when you can build a spreadsheet. You can type in the diameter, and the next day you're asked to do one with a different tank diameter. Well, you just type in a new number and you've got it done. So that's not really just a spreadsheet calculation anymore. It's a tool. And so I want you guys to be thinking, like, how can I convert my knowledge of Excel to building tools? What you really are is you're programming without writing any code. So you're making programs that can do these conversions and everything for you, and can optimize things, and you're doing it using a tool that you will all have access to. Yes, I could teach you how to do this in Python. I could teach you how to do this in various computer languages, but you may not have access to those at work. But you should have access to some sort of spreadsheet, most likely Excel. So today we're going to talk about the Hansen solubility sphere or interaction sphere analysis. They call it a solubility sphere, but your substance may not dissolve. Okay, maybe like a glove material. And so what we would be looking at is what is the group of solvents that might attack and go through a glove, or a gasket material. If we want to have an O-ring or a gasket between two surfaces, what is the solubility sphere of that gasket? So that if a fluid flows through and that gasket is supposed to seal that interface, if that fluid dissolves that gasket, it's going to go into the gasket, swell the gasket, maybe leak, maybe cause the gasket to break. So that'd be more of an interaction than solubility. It's probably not going to completely dissolve the polymer. It's probably going to swell the polymer or crack the polymer. So we're going to be talking about this solubility analysis. Oh, and let me just make a comment here. A lot of times your advisors give you literature reviews, early on in your project. And I know I was a student too. I always thought, well, this is busy work. They don't really know what to tell me to do. They want me to read the literature, and they're just kind of just telling me, here, go read some literature, right? Well, it's not true. As faculty members, as busy as we are, we're not always out there digging through the literature. And so when we send students out to do that, y'all are sort of catching up with what's current and informing us. It's a great way to multiply. It's really a team-based approach. So I was doing an explosives project, and it was a solubility of explosives project. They had 3 or 4 main solvents that they used to formulate these explosives, and they wanted to see if there were other solvents that would be better to use. And so they were asking me to analyze the solubility analysis. And so I sent these students out, in particular Katie Roethlisberger. She went out and started looking up solubility, and she came across the solubility parameters, the Hansen solubility parameters. And so she came to my office and she says, why aren't you using the Hansen solubility parameters for the solubility project that we're working on? And I looked at her and I said, what are those? I had no idea, because they weren't taught in academia, because they were developed in industry. And a lot of that stuff happens. And if Hansen hadn't published his work, then it would have just stayed in industry and nobody would know about it. Industry has a lot of internal publications. Like if it's a big company, they do a lot of research and development, but a lot of it stays internal. If the company does publish it externally, a lot of times it doesn't get picked up by academia. And if it does, a lot of times it goes into the research groups in academia, and they continue to publish with those things, but it doesn't ever make it into the curriculum. And so this is one of the few places you will actually get this in your curriculum, of analyzing the DP&H values and solubility, because I find it's a great way to look at the interactions of molecules. And then these other students used it in their research, so I give them credit for developing some of this. So this is the spreadsheet that we built. So spontaneous mixing and cohesive energy density. We've talked about the Gibbs energy, of course, that the entropy is positive and enthalpy is what typically prevents spontaneous mixing. And Hildebrand and Scott came up with this idea of a solubility parameter. Now theirs was limited to just the hydrocarbons. And so then Hansen came in and added in the DP&H values, polarity, dispersion, and hydrogen bonding. But it's based on this cohesive energy density. So think about this term here, this energy density. Yeah, this energy density term. So think about it, it's joules, that's energy, okay, per volume. So instead of density, like mass over volume, this is energy density. And so this is the delta H of vaporization. So remember, that's related to the intermolecular attractions, how much energy it takes to completely separate the molecules in a condensed phase. And then how dense is that? Like, per volume of a mole of that substance, how much energy is contained in that volume, in the cohesive forces between the molecules. Okay, this is the square root of that cohesive energy density is the solubility parameter. And so this is their estimate of the enthalpy of mixing. So notice that this difference in solubility terms is then squared, so that's positive. And so then we end up with this cohesive energy density. Okay. Now then that's energy density, that's energy per volume, and then it's multiplied by the volume. So now it's an energy. And then this is the mole fractions or the volume fractions of the mixture. So let me just put this up here. Okay. Okay. So that would be the amount of substance 1 divided by the total. Okay. So then the maximum, so these are all less than 1. They go from 0 to 1. And so the maximum value would be a 50-50 mixture. So that would be the largest enthalpy. It'd be a 50-50 mixture of these two. If the solubility parameters are too far apart, so that means this delta right here. So this delta right here, if that difference is too large, then the enthalpy is going to overwhelm the spontaneity because it's going to be a positive number. There's no negative numbers in this whole equation. That's one of the downfalls of this theory, is that you won't ever have negative enthalpies of mixing. Okay. Now units. We see these solubility parameters here. They're typically reported as megapascals to the 1/2, right? Because it's the square root of that energy density. So that's a weird unit. And you're looking at that. I don't know why they chose that as the SI unit for this energy density. It's a pressure. That drives me crazy. When it's exactly the same, equivalent as joules per milliliter or kilojoules per liter. That's an energy density. So if you tell me joules per liter or kilojoules per liter, I know it's an energy density. You tell me megapascals, what on earth is that? It sounds like a pressure, right? So here's how you get from joules per mil to pascals. Obviously, if I go from milliliters to liters, that's 1,000 joules per liter. Then I have that conversion from the ratio of the ideal gas constants, right? I have 8.314 divided by 0.08206. One's in liter atmospheres, the other's in joules per mole. And so this is that conversion, 101.325 joules per liter atmosphere. And then converting from atmospheres to pascals is 101,325 pascals per atmosphere. Okay, so the atmospheres have canceled, the liters have canceled, the joules have canceled, and we're at pascals. Now I have a factor of 1,000 for this joule, and I have 101,325 divided by 101.325. And so we can cancel those things, but don't forget the 1,000 there. So this is 10 to the 6th pascals or megapascals. So it's exactly the same number. So if I have 5 joules per mil, that's 5 megapascals. Yes?
Why did you research
You got it, yeah. This one here, that step's kind of weird. Yeah. And so so that's the unit we see in the tables. So if you go look up the Hansen solubility parameters, it'll be water has hydrogen bonding of 42 megapascals to the 1/2 power. That's stupid in my opinion. Right? Joules per mil. So many joules are in a milliliter of water that you had to pull apart if you're going to vaporize that water. Makes sense? That makes much more sense than the pressure. But anyway, that's the way it is. Might as well complain about the weather. Okay. So these industrial applications, this is used in the paints, coatings, and finishings of surfaces too, because the surface has a certain surface energy and the solvent has a certain energy associated with it. And this is also, this cohesion will affect the adhesion of the paint and coating to the surface. It'll also determine how well you can clean a particular soil off a surface. So if you have an oily contaminant, water's not going to touch it because the solubility parameters of water and oil are so incompatible. You put a surfactant in there, you may be able to bridge into that oily layer and pull it off. Or if you use a solvent, if the solvent matches the parameters of the soil, then it'll dissolve it right off. And we saw that last time with the cleaning applications. Okay, it was developed as a way to predict if one material will dissolve in another, just like dissolves like, right? Okay, so this is energy density. We have those three terms: dispersion, forces, polar forces, and hydrogen bonding effects. And so these solvents can be plotted in a three-dimensional Cartesian pattern. And these plots are a little different than what I've shown before. They're the same solvent places, but this is done with Povray. It's an accurate 3D rendering of this space. And so let's zoom in, and I'll show you why I like this particular plot. So this plot is more, I guess, intuitive to your brain because we have shadows. So like if we're looking at IPA here in this three-dimensional space, we can see that spot are the DP and H values for isopropyl alcohol. But you can also see its projection onto this wall. So that's the shadow of that dot. And so in this plane here, we have the H axis and we have the P axis. And so we can see its relative H values to these other solvents, and we can see its relative polarity to these other solvents. Back here in the back, acetonitrile, it's this one right here. So we can see that's a very polar solvent. You've got a methyl on one end, and you've got a nitrile on the other. And so I don't know if you know acetonitrile. So it's CH3CN. Very huge dipole moment. Okay, but for some reason, that lone pair on the nitrogen doesn't hydrogen bond very well because it's way down here on the hydrogen bonding axis. So I think that's kind of interesting that we have such a polar solvent, but it's purely polar and not hydrogen bonding. So hydrogen bonding and polarity are not the same thing. Okay. We can also look at the vertical shadows. So this IPA, if we come straight down, it's this ball right here, and it's very similar to ethyl acetate. So ethyl acetate, in terms of its polarity, ethyl acetate and isopropyl alcohol are almost the same. And also in terms of dispersion, they're also the same. They're very different in hydrogen bonding. So it's just a nice way to plot these things with the shadows. You see the projections onto the different planes. And anyway, it's not difficult to make these plots, but someone needs to teach you because I've got a special spreadsheet that generates the code for this Povray program. So this is POV Ray. It's what they call a ray tracing program. So it uses the physics of light to trace all of the rays of light in this three-dimensional space and produces the shadows and everything like that. This is the same general software engine that they use for making all the Pixar movies and these three-dimensional animations, Despicable Me and all of that. Yeah, great shows. Okay, so let's talk about this solubility sphere idea. So we need to do some things these calculations. I call this the Hansen distance. It's sort of a recognition of his role in solubility science. So I call this the Hansen distance. And I even sent him an email and asked him if I could, in my presentations and teaching, label this the Hansen distance, and he was very honored. He wrote back. He's like, "Oh, I would love for you to start doing that." So, all right, because it looks like the Euclidean distance, right? In X, Y, and Z space, right? You have the difference in X squared, the difference in Y squared, and the distance in Z squared, but it's different. What's different about this one? And this is not the Euclidean distance. Otherwise, I would be just relabeling the Euclidean distance with Hansen's name, and that wouldn't be appropriate. So this one's different in some way. Something should stand out to you when you look at this equation. What's that?
Yeah, the 4.
Yeah, the 4. What on earth is this 4 for? Okay. Question. That's what a lot of people have criticized his theory about. They're like, why do you have this 4 thrown in there on the dispersion term? Okay. And I'll draw that for you in a little bit. Okay, so we'll come to that 4 in a little bit. This dispersion term is weighted by a factor of 2, and we'll see why in a second. So that relative energy difference number, this is another piece that we will calculate. So this is if it's a sphere, right, it's going to have a radius r0, and so this is the radius of the interaction sphere. So we can take the distance of every solvent. So we have the solute and the solvent. We can take the distance between the solute and the solvent and compare that to the radius of the sphere. And if that distance is farther than the radius of the sphere, it's outside the sphere. And if it's less than the radius of the sphere, it's inside the sphere. So this is determining whether it's a good solvent or a bad solvent. The good solvents will be inside this sphere, this interaction sphere, and the bad solvents will be outside. Makes sense. Okay. Now, we will see in a second, I'll walk through the spreadsheet, what's going on with this solver thing. We don't know the radius of a particular substance. And sometimes we don't know the dP and H values for a substance or a surface. In this particular example, we're going to be looking at glass. So we're going to put various solvents on glass and see how they spread out. And we're going to try to come up with the dP and H values and this radius for the surface of glass. So we could find good solvents for wetting glass and bad solvents for wetting glass. And then we have a fit function. So we will optimize these values using solver in Excel. And so that would be one of the tools that you would learn if you come up with the sphere program in Excel. So this is our example, solid liquid interaction sphere. So we're going to put solvents on glass, and so this would be bad and this would be good. Okay, and so this would be a score of 3, and this would be a score of 1. And then 2 would be something in between. Okay. Make sense? Okay. So this is other things we could do. Instead of glass, we could do the same kind of analysis on gloves. We could take gloves, maybe in the past I've put them over a petri dish so they're stretched, and then I'll put the different solvents on there and see if it soaks into the glove or not. You know how important that is. There was a famous case. Her name was Wetterhahn. She was working in the hood, taking reasonable precautions. She was working with dimethyl mercury. So do you know about dimethyl mercury? It's mercury, right? But it's an organometallic substance now, and it gets in the body, and it's if you get mercury on your skin, it doesn't really go through your skin, and it beads up, doesn't interact with the skin. You put methyl groups on it, goes right through the skin. She was wearing latex gloves. She was pipetting, and she noticed that she dripped some on her glove, and it soaked into the glove. The glove didn't protect her. And she took it off, and it had gone into her skin. She calculated that she had received a lethal dose of mercury, and it took her about a month to die. Yeah. And there was no way for them to get it out of her system. They tried chelation therapy and all of that stuff, and it still killed her. Yeah. So latex gloves are worthless for anything other than aqueous solutions. Organic solvents go through them organic solvents love latex. It'll go right into that glove, and then it goes right into your skin if it's one that passes skin. And there's a model that, so there's Charles Hansen and there's Stephen Abbott. And Stephen Abbott, and then there's their ebook that you can see on Blackboard. If it's not on there, I need to talk to you. I need to put it up. They have a whole chapter on skin permeability, okay, for transdermal applications and things like that. And so they have a Hansen solubility parameter model for skin, so you could determine if this solvent is going to go into your skin or not. And so it's valuable. So will the solvent wet the surface? Will this polymer go through your skin? Are these two surfaces similar? Are they clean, etc.? So we can use these kinds of trials to determine all these different kinds of questions. It's a very simple procedure. You prepare the surface, put a drop of each solvent on the surface, score the interaction. So 1, it spreads out, soaks in. 2, there's some spreading or soaking. And 3, no spreading at all, no soaking. It doesn't spread out onto the surface. So this is just our solid liquid interaction scores. So what we do is we gather a range of solvents. Now, what is a good range of solvents? It's not just a big list of solvents. You want solvents that have different D values, P values, and H values. So notice these go, there's the smallest one, it's like 14. Do I have any less than that? 14.9. Sometimes you can get even a more of a bigger range of solvents. This is only 15. I typically do 20 to 25, but it goes up to 20 in terms of the D value. P values go from 0 to 18, it looks like. And then the H values go from 0 to 42. So water's 42. So we've got a range of all three because we want a nice cloud of solvents, and our surface will be somewhere in that cloud of solvents. Does that make sense? Okay. So we collect those. We have them all in little individual jars, little pipettes ready to go, and then we just take a drop of each of those solvents and we score them. So we score them, we expose the test substance to each solvent, score the interaction. For solubility, let's say I wanted to determine for those explosives, I take a little bit of explosive in each vial. So I would weigh out maybe a tenth or 0.2 grams of my powder. And if you have a polymer or some kind of substance in your research that you want to find a good solvent for, or find the DPH values for, get 20 solvents, 20 vials, put a small amount of your substance in each vial. Then each solvent goes in there, and you can count the drops. You can do it by mass too, but you can put a drop of solvent in there and shake it and see if it's homogeneous. Some solvents will dissolve your 0.1 gram of substance with one drop. That's a good solvent, right? You shake it and you look, it's homogeneous, mark it down. That's a 1, okay, on the score. Some you just keep dropping. You fill the vial halfway. You look, you still see powder in there. That's a bad solvent. So mark down a 6. And so it's all you just got 1 through 6. In this particular example today, we just have 1 through 3. But the traditional model in Hansen is you got 6 demarcations, or you could do 5. It doesn't really matter. 5 stars, right? You pick. It's a really good solvent. You want to pick the low numbers is good. So maybe a 5 stars is not a good, doesn't have a good connotation. So anyway, you score them. And now look at our scores. Up here it's saying acetone was good. Okay. Ethyl acetate was okay. Hexane was good. IPA, MEK, methanol. So these are the scores. Toluene was okay, wasn't good. But these are the scores of solvents that spontaneously spread on glass. And these are the solvents that didn't, okay? So we go through, we score all of our interactions. Makes sense? Yeah, okay. And then we do this. This is an initial guess, okay? So we take the ones and we see the D value. We got like a 15 here, 15. We got some 14s, okay, 15, and then an 18. Now, this is not really a great guess as 18. I would have probably picked something closer to 15 or 16, okay? But anyway, this is an initial guess. I would typically pick one. You might even in Excel just average all of the good ones, put the average up there. That'd be a really good guess. For the polar, you go through again. You've got 10 here, a 5, some zeros, a 6, a 9. And so the initial guess was 8 here for the polar term. This water one, you got 42 here, and you got some zeros here. So, that's in between 19. So do you see what we're doing? We are choosing the DP and H values for the substance of interest. In this example, it's glass. In your example, it might be your polymer or whatever that you're trying to find the perfect solvent for. Okay. Your perfect solvent does not have to be in this list. It's great if it is, but you get this cloud of solvents, you test the interaction with this cloud of solvents, and then you know about your substance. And then you can find the solvent that's the best. Okay. That's R0 is the thing that confuses most people, because there's nothing on this sheet that allows you to guess the R0. You can't take an average of something or whatever. So you can start with, I would say, start with a small one. This one's too big. I might start with an R0 of like 4 or 5. Okay. Okay, for R0. So 10, I think that's way too big. But and so next we're going to optimize our test substance DPNH and RO values to draw a sphere around the test substance that contains the good solvents and excludes the bad solvents. But if I start changing these numbers, nothing depends upon them. So I've got to come up with some equations that depend upon those numbers that tell me if it's good or not. So right now, I don't know if the sphere is located in the proper spot, and I don't know if the radius is proper. So I've got to optimize the radius so it captures the good solvents, and I've got to put it in the right spot so it both excludes the bad ones and includes the good ones. Okay. So now the next 4 or 5 columns are the optimization columns. Okay. So first we need to calculate the distance of each of these solvents to the substance I'm looking for, right? So up here is my, up here is my DPNH values for the substance, and then here's each solvent has a DPNH value. So this would be the solute up here, using that equation, the terms in that equation, and these are the solvents. So I can calculate this RA value. Okay, I'm still pushing that 4 off till later, okay? All right. And so then it's Excel, so we make that equation once. It's kind of tedious to go and click all those cells, but then once you do it, you double click and it goes down, and you've got to copy it all the way down. All right, then the next column, this relative energy difference, or relative energy distance, density here, and it looks at this RA and compares it to R0. Okay, and so some of these are less than R0, like 9.6, less than 10. And so this is less than 1. And so this one is going to be called a good solvent. This one's a good solvent. This one's a good solvent. Okay. And so you can kind of see that some of our 1s are captured as good solvents. This 2 is not, and this 3 is not. Okay, but look at this 3. That's not good. Bad. Okay. Okay. So we know that our DPNH values and the R0 up at the top are not right, okay? So we need to find a way to optimize them. Now we could go up there and change it by hand. We could see like which one of these DPNH values is giving us a problem, and we could move the D value and the P value and the H value. And that's really tedious, okay? Because you've got 4 variables and you change them one at a time, and it's a pain. Yes?
Yeah. The other time you said if you change the R0, that R0 value at 5 is good. So if the R0 at 5 is good and you change this from 10 to 5, some of these good, some of these bad solvents will be good.
Yeah, and so we will see why 5 is a good starting point, and then we'll let it modify from there. So again, these up here that we started with, these are just our initial guesses, and then they will be optimized. Okay. So now the next column, this is the linear distance from the surface of the sphere. Okay, so this is telling us how bad and how good it is, right? We're just taking the sphere distance and RA. So if it's greater than R0, how much greater is it? And if it's less than R0, how much less is it? So it's just the distance from the surface of the sphere. If it's right on the sphere, it's not a bad problem. But if it's really far, if it's a good solvent that's way far out of the sphere, that's a real problem. And if it's a bad solvent that's really inside the sphere, close to the center, that's a terrible problem. Okay, so we need to know how much of a problem our situation is, and that's needed for this fit function. Now we have this. What do you want to call this? The score is sort of a 1 to 3 scale, or sometimes it's a 1 to 6 scale, but we really just need a good or bad. Like we need to decide which of these numbers we're going to call good. Is it just the 1s, or is it the ones and the twos? Or if you had a 6-point scale, you might include the threes. So you might include the ones are inside always. Or is it the ones and the twos are inside, or the ones, twos, and threes are inside? Sometimes those judgment calls, especially in solubility, you're looking at it and you're like, that could be a good solvent. Maybe it's not. And so you might refine which ones you call good and bad right on the fringe cases. Okay. And so that's what this column is for. We're just reducing it to a binary choice of good and bad. So we notice that this is a 1. Okay, so we're flagging that one as a 1. But look, this one's a 2. We're going to say, yeah, let's call that 2 a good solvent. So in this case, the flags are including the 2s as good solvents. Okay. And then we have this prediction. So we're looking at, and it's an if-then statement. So this uses the Excel, this is the Excel formula here. We're just looking at this column here, and we're saying if red is less than 1, then it should be 1. It should be flagged as a 1. And if it's not, it should be flagged as a 0. So this is not less than 1, so it should be flagged as a 0. And so we can easily compare these two columns. What we flagged as good and bad, and then the predicted good and bad. And so we're just setting this up so that we can use an if-then statement in order to come up with our fit function. So here's our fit function. So this is the Boolean operator. We say if the predicted equals the flag, then we're great. Okay, so we've got if predicted equals flag, then AI, this little fit term, is going to equal 1. So we can see over here, the flag was 0, the predicted was 0, so AI is 1. Here, the flag was 0, so we call that a bad solvent, but this predicted from our DPNH and R values, our 0 values, it's saying that this solvent is inside the sphere, okay, and so that's a problem. So when it's a problem, we calculate how bad the problem is. It's the exponent of the minus of this difference, this absolute value difference. We don't want it to be signed in terms of inside or outside of the sphere. So we take the absolute value of that difference and then we make it negative. So it's this exponential. It's a maximum of 1 and then it goes down dramatically in an exponential fashion. So we have all of these little individual terms. So we're saying this one's good, this one's good, this one's kind of good, it's 0.7, but this one's really bad, 0.05. And so how do we know, how do we sort of take this whole column and come up with a single number that gauges how good our fit is? Because we have 15 different values. Some are perfect, some are terrible. And how do we capture how bad it is when we have multiple terrible numbers? We just multiply them all by each other. If they're all 1s, the result is 1. If they're all 1s and I've got one really bad one, that really bad one is going to cause my fit to be really bad. And it's going to get a lot of emphasis. And so this is a way to set this up. You see, this is the fit is the product of all of these little AIs. And if everything's good, the predicted and the flag match, then I get AIs of 1. All of the 1s multiplied by each other, I get a fit of 1. This is how we do it in Excel. So this formula right here is this formula. So this formula goes right here into that cell, and you multiply all of those down. And then this fit function here is just the product of all of those straight down the column. Okay. Now, we've got a fit of 0 because our numbers are terrible. Okay. And so we could go in and we could change those 4 cells by hand and see how the fit gets better. Okay. But that's super tedious. Okay. So let's have Excel do that. It can do exactly the same thing, change all 4 of those values and watch the fit value, but it just does it at 1,000 times faster than us, or maybe a billion times faster, gigahertz, right? So we've got our target cell, L3. So our target cell is right there. So we're changing L3. We want a fit value of 1. So you can say maximum, minimum, but we want a value of 1. So we want it to go to 1. And then what do we do? By changing cells, C3 through F3. So you see these cells right here. We're telling solver, change these cells until the fit value equals 1. You hit go. It typically behaves well. There's some times when, like, it wants to push the D values to negative values, and none of these solubility parameters are negative, or it'll push the polar values negative or the hydrogen bonding values negative. A lot of times it's the D and the P values that typically try to go negative. And so you could add constraints here. Let's see. So if you hit add, you could put in here that D. Let's see, C. Let's see, C. Let me change that. C3 must be greater than or equal to 0. Like, you could put that in, so when it goes down, it'll hit 0 and it won't go below, and it'll just peg and it'll change the other numbers and so on. So you can add some constraints. Another thing I think is really helpful is to not include R0 first. So like this one should probably be 5. So you got kind of a small sphere, and don't optimize R0 when you first do this. Okay, so what we're doing is we're starting with a small sphere, and so it won't even include all the good solvents. Okay, so we're not going to get a perfect fit, but we're going to get the best fit we can. And it's going to move that sphere into the middle of all of the good solvents. Because if it's not in the center of those good solvents, then a lot of those R values are unnecessarily large. So if it moves it to the middle, they're all just very close to the outside of that sphere. So you've got a good fit, as good a fit as you can get. And then you let it expand R0, like you might even go to 5.5 or 5.6, or increase it a little bit and redo solver, and it'll move it around into the middle until you finally get one where it just includes the good solvents, and I call that the minimum R0. And so once you have that, it may not be the best version of the R0, but it's the minimum one that contains all of the good solvents. And so that's how you get the minimum R0 with your set of solvents. And that's going to be a great determination of the DP and H values. I've been using this, almost 10 years now. And it has really allowed a lot of fantastic work in protecting polymers, determining what gloves are interacting with different solvents, being able to dissolve different explosives, being able to predict the outcome of recrystallizations. So it's been useful in a lot of areas, and that's my technique. I let it have free reign on DP and H, and I fix R0. And then I expand R0 a little bit and a little bit, and then it does well. Once you hit a fit function of 1, then it's fine. Now notice you'll get a fit function of 1, a result of 1 in many different scenarios. There can be a fair bit of slop. Let me find it here. So this is the one we did for glass. And so we had methanol, ethanol, isopropanol, and then some of those organic solvents down there. And so the glass interaction sphere was right here. And this was the radius. It was a pretty big R0, and excluded the bad solvents, included the good ones. Now, this has an absolutely huge radius, but still, this was the function that we got for glass, and it was able to get a fit of 1. It was able to exclude all of the bad solvents and include all of the good ones. Sometimes, though, there's let's just say there's a couple of good solvents. I'll just indicate those by check marks, and there's a bad solvent that's an X. And you can draw the minimum sphere that includes those. Okay, so that would be the minimum R0. and you don't hit a bad solvent until you're way out here. And yet both any R0 between those two would give a fit function of 1. So this is an artifact of the solvents that you chose. Maybe there's a solvent right here that was not in your solvent list. And so you really don't know which is the best R0 because you don't have the perfect list of solvents. So I'm fine with picking the minimum R0, and nothing substantial, I would say, ever really depends upon R0. You really, when you're coming up with blends and so on, you're trying to get closest to the center of that sphere anyway. So it's the center of the sphere that's driving your goal seeking in the experimentation. So whether you have the maximum R0 or the minimum R0 is not that important. What's important is the center of that sphere, because that's the identity of that substance in terms of DP and H values. Does that make sense? Okay. So in terms of using the solvent blends, these are how the solvents are blended together. Oh man, it's 9:50. Okay, well, we'll do blends next time. It's a good time to break, but I'm sad because, yeah. All right, so we'll talk about blends next time. Glad I looked at the clock.